Yeah, I'm going to talk about some work sort of in the direction of and with the hope of a lot of future work in the space of interactive natural language processing. I'll say at the beginning, I think interaction is good. So please interrupt me at any time with questions or comments or anything. Just unmute yourself or whatever is most convenient for you. So I'd love to hear other people's thoughts and questions. All right, so let's sort of dive in. There's been a lot of success in natural language processing recently. So we now have sort of like automated voice assistants. This is a picture of the car version of Siri. We have things like machine translation that people use on a daily basis to communicate with people in other languages. We have systems that try to guess what you're going to say to make writing email more efficient. And there's obviously, many more examples like this. In fact, like a couple of years ago, World Bank data recently measured uses of AI technology and found that between voice-based systems, virtual assistants, and other language-based medium, this is one of the largest growing sort of consumer technology spaces that there is. But I think, like, at least speaking for myself, as someone who sort of comes from like a technology background, when I think about these technologies, I sometimes forget about the fact that by virtue of being a language system, any system we build like this has a user embedded in it somewhere. And then beyond that, because language is fundamentally a human and social endeavor, language processing systems, have both sort of direct users, like the one who's like typing the email, as well as a sort of whole society of users that are impacted by this technology. So I like this quote from Marty Hurst in IEEE Information Systems. So she points out that in the last few years, a series of well-publicized debates have been basically around this question between total automation of user needs, typically by intelligent agents, versus systems that give user control and decision-making to people via interfaces. So I think it's accurate to say that I've heard a lot of debates about this in like the past couple of years. The thing that may surprise some people, but maybe not everyone, is that Marty actually wrote this in 1999. And so, I think it's fair to say that this sort of debate is ongoing. I think to some degree it was won early on in the sort of user control and decision-making side of things, but with this recent burgeoning of fully autonomous systems that actually seem pretty capable, I think this debate is coming back. So more recently, papers by Wing and Schneiderman have contributed to like a more recent version of this debate. So I want to talk about sort of this tension between automation and user control and decision making in the context of natural language processing, because that's what I do and what I'm interested in. But specifically in the context of document triage, sorting, and the example I'll be giving is from automated content moderation. But you can think about this in terms of sort of any task where there's a person, the person receives some sort of document, and they need to make quick decisions about this document. So in this setting, the person gets a document. In the content moderation case, they might need to flag this document for one or more violations of community norms. So these are the community norms in the Reddit subreddit Ask Historians. So things like it violates civility, it's too shallow, it doesn't cite its sources, on to things like plagiarism, moralizing, and just humor. So to sort of make this a little bit more concrete, I'll give an example of a post that a content moderator might have to deal with. So I won't read this whole thing, but it starts out, "You must not come out much." even a cursory glance on news outlets should instill you with the idea of just how brutal man can still be, but I understand why some people must think such. Imagine growing up, blah, blah, blah. So the moderator's job in this case is to figure out if this violates any of these community norms, and if so, which ones, so that this content moderation decision can be accountable both to the person making the post, the other members of this subreddit community, and potentially as training for future human moderators. Okay, so this is a hard task. And so what we might want is some sort of agent that can help the person do this job. So we could imagine this sort of as a dialogue where the system says, not necessarily in English, but says something like, you know, this appears to violate both anecdotes and plagiarism, and maybe like, here's the evidence that I have supporting that, that assertion. Maybe the person actually realizes that this thing in, you know, the paragraph is not actually an anecdote, and really doesn't understand why the machine thinks that this violates the plagiarism rule. So then maybe the system would come back saying, you know, here's a document that contains almost exactly the same content as in paragraph 4. And then based on this, the human maybe makes the final judgment that this document violates 2 rules. One is plagiarism and one is moralizing. And I'm going to tell the original poster, you know, what in their post was led to this assessment. So the thing that I want to sort of emphasize here is this difference between sort of the fully autonomous system, where you might just hand off all content moderation decisions to an automated system that's trying to solve the task by itself. Its aim presumably would be to outperform or at least perform comparably to humans, but much more efficiently. And really doesn't do much by way of communicating the decisions that it makes, aside from like, I predict that this is plagiarism. To something that's more like an assistant AI that's trying to cooperate with humans to solve the task. That also sort of obeys and aids the people in tasks that it's better at than humans are, for instance, the plagiarism example. And also hopefully communicates naturally and faithfully with humans, so that content moderators, who generally speaking are not technology experts, don't have to, you know, learn an entirely new way of communicating with this assistant, but can rather do it, you know, through a medium like English that's natural to them, or another language if that's appropriate for the person. And I think this sort of trend of going from autonomous to assistant is reflected in a bunch of subfields of AI these days, whether it's sort of this framing of human-centered AI or cooperative AI, work on bias and fairness, and then work on explainability. And I think all of these are sort of like biting off different pieces of this puzzle of how do we get to assistance rather than full autonomy. So, you know, my perspective is sort of like a language person, is that if we want to give the user control, we need to be able to allow for sort of rich communication between the user and the system. So the user needs to be able to make requests, give instructions, provide additional context, clarify things, add missing information. The system also needs to be able to sort of make predictions, explain its decisions, ask questions when it's unsure, provide context, and also deal with missing information. So fundamentally, this is largely about coming to some sort of like common ground between the user and the system through the various communication mechanisms. And while this is happening, presumably both of these systems are also learning. So the human is learning how the machine works, the machine is learning what the human wants. And so all of this needs to be done in a process where things change over time. All right, so that's sort of the like big picture of where I want to get to. We're not there yet. So for sort of the technical meat of the talk, I want to talk about basically 3 projects that aim to make progress on various aspects of this bidirectional communication. And they're all in slightly different settings because basically because you go where the data is available. And so, so we'll jump around between topics a little bit. So in the first, I want to talk a little bit about getting agents to be able to ask for help when they're unsure of things. So this would be like the example of, actually, I don't think I had an example in the previous one. So this requires them to know when they're uncertain and also to be able to communicate that uncertainty in a reasonable way. After that, I want to talk a little bit more about explainability. So instead of asking for help, I want to enable the agent to explain its own behavior. And then last, I want to talk about mostly ongoing work, sort of broadening these questions of like, what does it mean to explain? How do we learn from feedback that include both human and machine explanations of decisions? So in all of these cases, I'm showing pictures of the students who were involved. In some cases, there were non-students involved in these projects. They don't get their picture up because I don't know, it's not as important. I think it's more important to highlight the students because they're the ones who actually did the work. So I'll start off with this piece about training systems to ask for help. So this was with my former student, Sudha Rao, and my current student, Kan Wen, who is graduating this summer. So he's probably going to do a postdoc for a year, but he'll probably be on the job market next year. If anyone is interested in hiring him, I'm sure he would be interested in talking about it. But I guess before I dive in there, maybe let me just take a quick pause to see if there's any questions so far.
Any questions? If you have any question, you can also type in the chat box, or you can ask Dr. Daumé.
Okay, if not, I'll go in. So asking for help, right? So the setting I'm imagining here is something like the machine says this article appears to be about tensions in Ukraine, but I can't tell if it is the current event or the war from the early 1900s. And maybe the person has additional context that enables them to identify that this is about the historical war, and therefore it's not violating this prohibition of talking about current events. So in order to do this, the agent needs to be able to do two things. It needs to be able to predict when it doesn't know, and also ask for help, and ideally ask for specific help so that it can tell the person what it is that it needs from them in order to make progress on helping. So we started this work, I guess it was like 4 or 5 years ago now, where we're looking at specifically asking for clarification questions. So the setting we were looking at there was not content moderation, but seeking help on online fora like Stack Exchange. So this is from Ask Ubuntu. So someone's asking, how do I configure the path or set environment variables for installation? They have some post. And one of the norms on Stack Exchange is that if the post is not sufficiently detailed in order to provide an answer, people make a comment where they might ask a question. So a person might ask a question like, what version of Ubuntu do you have? And then what's supposed to happen is the original poster goes back and edits the post to answer the question to make it sufficiently specific that help can be provided. So we can extract this basically through an edit history of original post, clarification question, and then edit to the original post, which we're going to treat as an answer. So to sort of motivate the approach that we're going to take, let's think about this example and think about 3 potential questions that could be asked to help provide an answer. So the actual question that was asked was, what version of Ubuntu do you have? 2 other possible questions that could be asked. So one would be, what is the make of your Wi-Fi card? And the second is, are you running Ubuntu 14.10 kernel, blah, 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 blah. And so, I could do a poll. Hopefully people generally think that the first question here is probably the best question to ask. And intuitively, the reason why the first question might be a good question to ask is because the second one doesn't seem particularly relevant. So an answer to this question is unlikely to help provide a better answer. The third one seems sort of unnecessarily specific. Like the answer might be yes, in which case great. But if the answer is no, then that gives us so little information that it's not really going to help us help the user solve their problem. So the way that we're going to capture this is through expected value of perfect information, which we're going to model through a neural network approach. So the expected value of perfect information is this pretty classic idea from AI that basically says, when I don't know the value of a variable, let me try to guess, and then ask how useful would it be if that guess was correct. So in this case, I'm asking for some post P and potential query QI. So QI is like, what version of Ubuntu are you running? How much do I expect that query to help get a useful answer? So this basically says that the expected value of perfect information for this query given this post is an average over all possible answers I could get to that question. First, of how likely is that answer? And second, how useful would that answer be? So in the previous example, asking about the Wi-Fi card might have a high probability answer, but that answer might not be very useful. Whereas the very specific question about the version of Ubuntu might have a very useful answer, but that answer is going to be low probability. And so a good question, like what version of Ubuntu are you running, is one where there's many answers with high probability, and many of them give high utility. So this means we have to estimate two quantities. So one is the probability of an answer given a post in question, and the second is the utility of an answer being added to a post. And so both of these, this was 2018, so this was like pre-transformer days. So we use bidirectional LSTMs and sort of the standard stuff back at that time. But we essentially train the probability model based on this data set of post-question answer triples that we have. And we train the utility classifier based on post and answers. So we evaluate this in a bunch of ways. So this first one is precision at one, which is just, is the top question selected by the system marked by people as a good question or not? So these numbers are generally pretty low. They're like in the 20s, but that's because this is a very hard task. So what we're seeing here is a bunch of results over sort of various versions of the system, starting at one that just chooses a question to ask randomly, up to the expected value of perfect information one. And the sort of most important comparison here is between the green and the light blue. So the light blue model is essentially a model that uses the post query and answer and has exactly the same number of parameters as the expected value of perfect information, but just treats this as a straightforward prediction problem. Is this the right answer? Is this a good question to ask or not? Whereas EVPI breaks this into the utility and the probability. And what we see is that this gives a gain of a couple percent in both precision and one, at one, as well as mean average precision and a bunch of other metrics that are in the paper. So the takeaway from this part is basically that given a collected data set where people have asked questions, where people have asked clarification questions, we can train a model to mimic the questions that people might ask to some degree. And in doing so, it's helpful to not just try to make a straight prediction, but actually try to model the process of what do I expect as an answer to this question, and will that answer help me make a decision at whatever it is that I'm trying to accomplish in general. But that setting that we considered there was fairly simplistic in the sense that it's just a single decision that the system is trying to make. And it's not particularly interactive. So the next thing we did was we took this into a more interactive setting where we have an agent who's trying to navigate a photorealistic environment to find an object in response to a human request. So the human might say something like, find a mug, and then the agent's job is to execute navigation actions in this environment to reach a mug wherever it might be in the house. If you take off-the-shelf algorithms to try to solve this task fully autonomously, you end up with success rates in the sort of like 10 to 20% range. So the fully autonomous agents are not very capable at solving these tasks, especially when placed in environments that they haven't seen before. So it turns out humans are also not that great at solving tasks. Like if I put you in a random house you've never been in before and I ask you to find a mug, you might not do a very good job at it. But one thing you can do is you can ask for help. When humans are faced with new tasks that they can't accomplish on their own, they have this nice robustification mechanism where they can ask potentially other humans for help. So you might ask like, well, where is the kitchen? Because you might believe that a mug is going to be in the kitchen. So the question is, can we teach the agent to figure out when it's made progress and to interpret the human instruction that it gets in order to make that progress? So what does this look like? So the agent might be given a task like find a mug. It might decide that it's gotten lost. It's going to ask for help. And then a human in the environment is going to give some instruction that's going to help the agent make progress on its task, although not necessarily complete it entirely. So I think that's actually what I just said. Okay, so this means that the agent's making two decisions at every step. So the first is whether to ask for help or not. And then if it decides that it doesn't need help, then it's just going to sort of continue on its own. And we're going to model this with this navigation policy, which we're going to call PyNav, which is basically choosing actions in the environment. If it decides it does need to ask for help, then it doesn't move in this step. It requests help, and then it receives this instruction, and then it repeats. So the question is, how do we teach it to do these things? So the navigation, so we're going to take sort of this imitation approach where we assume we have access at training time to an optimal policy, or at least a very good navigation policy, and we can train the navigation policy to just mimic this near optimal navigation policy. So in our case, this is going to be a policy that suggests the next location along the shortest path to the goal. So it knows where the goal is, computes the shortest path in the environment, and then it says, okay, the thing you should do next is blah. So given this, we can learn a fairly effective navigator. It's less clear how to train the model for learning when to ask questions. So in the previous work on clarification generation, we learned to replicate the questions that humans might ask, which is useful if you're a human. But if you're not a human, then the sorts of things that you might be confused about might be very different than the sorts of things that humans are confused about. And so what we'd really like to do is we'd like to ask for information that the agent thinks will help itself rather than what a human thinks will help a human. So we're going to do this in sort of two ways. So the first is to use sort of just an uncertainty-based metric. So if the entropy of the navigation policy is above some threshold, then we might ask. So the problem with this is that these sort of deep neural network things that we train these days are generally really poorly calibrated. So they might be like absolutely sure that the right thing to do is to turn left, even though they really have no idea. So where we really get the most leverage is by this progress-based teacher. So what we would like to know is for the agent at its current stage, if it made a decision, if it were to ask a question now, would asking that question help it make progress in the future? Now, at this current time, we don't know the answer to that question. But what we can do is we can let the agent finish its execution and then retrospectively look back and say, basically, where did things go awry? So if there's, for instance, any state where starting at that state, it never gets any closer to the goal, then we might say, oh, it probably should have asked in that state. And so this sort of like gold standard, or in this case, sort of like bronze standard training policy is one which requests help when either of these conditions are met. So either the entropy is high or retrospectively, the model's not going to make progress. Okay, so how does this do? So here on the y-axis, we're plotting the success rate. So how often does it actually succeed at the task? If the agent just walks randomly, it succeeds about 0.5% of the time. So this is at least a somewhat difficult problem. If you ask it to solve the task fully autonomously, in environments that it's seen before, it solves it about 17% of the time. In environments it's never seen before, it's about 8% of the time. So this is sort of the like fully autonomous version. If you give it the ability to ask for help, but it doesn't get language feedback, it only gets image feedback. So the assistance is of the form, here's a picture of a room that will make progress on your task. So like, here's a picture of the kitchen. So in seen environments, this helps a lot. So success rate goes up to about 85%. Basically because the agent has probably memorized the environment. And so when you show it a picture of the kitchen, it knows exactly how to get to the kitchen. But in unseen environments, there's a huge gap because you might show it a picture of the kitchen, but it has no idea where the kitchen is in this house. So in that case, having the language assistance as well provides a substantial bump in unseen environments and a sort of tiny bump in seen environments. And this is because getting this language feedback allows the agent to generalize to new environments where it hasn't already memorized where everything is. Okay, but that was just asking, that was sort of throwing up my hands and saying, I need help, please help me, which got away from this, let me ask for a specific question. So how do we get asking for specific questions back in? So like I said, we could follow this approach of mimicking what humans might ask, but that might not actually be helpful for the agent to solve its task. So instead, we're going to give the agent sort of this space of types of questions it can ask and allow it to formulate questions within that space. So the first is basically, tell me more about where I am now. So my sensors are imperfect. I don't know if this thing in front of me is a chair or a table or whatever. It might ask for more information about the goal. So maybe it's being asked to find a rice cooker. It has no idea what a rice cooker is. And so the person might say, oh, well, look in the kitchen. Or it might just be completely lost and just say, like, please, direct me to something that will help me make progress, in which case the person might give instructions to get to the kitchen. So which we formulate as basically a sub-goal state. So we formulate this question asking as a reinforcement learning problem where it has these options of things to ask for, and it learns to ask for ones that maximally improve its success rate at the task over time. Okay, so what does this look like in the human-assisted navigation? So, okay, caveat, the experimental setup here is a bit different from the previous one, so these numbers aren't comparable to the previous numbers that I showed. So here, the blue bar is the agent that has access to imperfect information and cannot ask for help. And the red bar is an agent that has access to perfect information but cannot ask for help. And what we see is that in known environments, but with new start locations, as well as known environments with new objects, being able to ask for help largely closes the gap between the agent with imperfect information and the agent with perfect information. And on unseen environments, the agent actually does even better than the one with perfect information. And this is exactly because it can ask for sub goals, and the sub goals help it significantly. All right, so let me take a break here and see what questions have come up. I actually can't see the chat, so if there are any in the chat, please.
I can read it for you. There is no question posted in the
I have a
chat.
question. I don't know how to use the hand raising feature in this application, but
Please unmute yourself and go ahead.
okay, thanks. Hey, Hal.
Hey, how's it going?
So yeah, I think this works interesting. First clarification question was, which data set we're using to do this work?
Yeah, so this is okay. So there's many answers to this question. So this is Matterport 3D.
Yeah.
For the instructions, we're using the room-to-room data set.
Room to room. Okay.
Yeah.
Yeah.
And
All
we're
right, yeah, room to room is go ahead.
sorry, actually, that's not quite correct. So for the first part where you're just asking for help, that's room to room. For this one where you're asking for specific feedback, I can't remember what it's called, but there's like an extension of room to room that came out like 6 months ago by a bunch of like Google folks. It's basically room to room, but like 10 times bigger. So we're using that.
Okay, sure. Yeah, I just was wondering, what do you think about agents in these tasks like vision language navigation or even vision dialogue and navigation, modeling high-level goals with neural models? Because what I've observed, I guess, in most of the work in this area is that they do a pretty good job at the, turn by turn and learning from the step by step. But then when you're trying to track a broader goal, like trying to bake something, using like, let's say it's a virtual kitchen environment, you gotta do a series of things to accomplish a goal. How could that work? Would you imagine using other sort of models, or would you try to learn everything in one larger, neural model?
Personally, I would be more interested in, sort of a more structured model for these harder problems. Like I think there's already issues where, so for instance, in these experiments, we have these sub goals, right? So the way this is implemented is the agent basically has a stack of goals that starts out with the original one, and then every time it gets a sub goal, it basically pushes that onto the stack. In this setting, it wasn't necessary to, so for this, we're using sort of like a transformer approach, and we're not giving it access to anything except the most recent sub goal, basically because it didn't help to give it access to the other sub goals. But I think for something like cooking or something like that, it might actually be really important that it knows that it's beating these eggs, because it's going to eventually put them in a frying pan versus it's going to, I don't know, like cream them with sugar to make a cookie or something like that. And so, I think, this stack representation is a very simplistic one, but I think it would be really interesting to think about more like complex, like I have my little note card that I'm taking notes of what I'm supposed to be doing and things like that. Yeah,
that sounds what I would also agree with what you're thinking. And you may have heard about this already. There's been some newer, a data set that just came out from Amazon, the Teach data set that looking at dialogue, and it's going to be using this Amazon Symbot challenge.
Yeah.
It's interactive, and it's there's going to be help and it's using. So one of the metrics they're using is the whole dialogue history. So how do you learn, like, to predict the next action for the agent from the entire dialogue history up to that point? So
yes, yeah,
because the tasks are more high level. So I think it's sort of in line with what you're thinking.
Yeah, no, I think I really like this task. I think it's super interesting.
Thank you, Matt. Any other questions? Looks like there is no more question.
All right. So let me move on. So that was about, how do we get the agent to be able to know when it doesn't know and to be able to ask for help from a human in the environment. So it's one thing to know when you don't know. It's another thing to sort of say why, or to say, why it is that I've made a particular prediction, right? So In our little content moderation example, we might want a system that says, something like this appears to violate both the anecdotes rule as well as plagiarism based on, these various parts of the input text. And that is a copy and pasted bubble that does not belong there. All right, so so this largely falls in, this space that's sometimes called explainable AI, sometimes called interpretable machine learning, sometimes called a whole bunch of different things. But at the end of the day, the goal is to explain something about the machine behavior to people so that people can make a better decision based on that understanding. And so if our goal is to help people make better decisions, it's probably a good idea to focus on the human needs, both in the design and evaluation of techniques like this. So it turns out that the nature of human explanations has long been studied in areas like philosophy, cognitive and social sciences. There's some citations there. And if you look through that stuff, there's a handful of principles of human explanation that emerge. So human explanations tend to be contrastive. So, I tell you why I did something as opposed to something else. They're often counterfactual and they tend to be sequential. So I don't explain my entire decision at once. I tell you some stuff, maybe you ask some questions, maybe I provide a little bit more information and so on. Whereas typically machine explanations are absolute and non-contrastive. There's some recent work looking at contrastive explanations as well. They tend to be factual rather than counterfactual, and I think almost everything I've seen is one shot. Although I don't want to swear to that. So the first thing we did was, based on this knowledge from various other fields of study, we tried to come up with a bunch of principles that explanations should adhere to. So the first is, why did I predict this thing instead of something else? The second is I should be able to decompose my explanation into simple building blocks. I should not bother the person with things that are irrelevant. I should present my explanation in terms of quantities that people can make sense of. And if I'm trying to explain one choice out of many, I should be able to uniquely identify the thing that I finally settled on, as opposed to everything else, not just some other things. So the way that we're going to instantiate this, and I'm going to point to the paper for more details on why this is actually a good match for all of those design principles, is this idea based on weight of evidence. So this is this idea from statistics that dates back to Pierce in the late 1800s, but was basically popularized by Good in the 1950s and 1960s, which says for some hypothesis H and some evidence E, how much does E speak in favor of or against H? So H, think about as the prediction that the model is making, and E is some aspect of the input, so like the sentences in the text or something like that. So this was originally sort of popularized by this 1950s book by Good, of Good Turing fame, if you are a NLP person who learned about NLP when we were still doing n-gram models all the time. Okay, so mathematically, what is weight of evidence? So there's two equivalent ways of expressing it. One in terms of log odds and the other in terms of conditional probabilities. So the hypothesis odds interpretation is, I say the weight of evidence of E in favor of H is basically saying that the odds that H is true are higher when I know E than when I don't know E. Or if the weight of evidence is negative, they're lower when I know E versus when I don't know E. By some, sort of straightforward Bayes rule calculation, this is equivalent to this evidence likelihood interpretation, which says that the weight of evidence corresponds to having a likelihood of the evidence under the hypothesis being higher than under the negation of the hypothesis. So basically, this hypothesis makes the evidence more likely than other hypotheses would. Okay, so what does this look like in practice? So here's a sort of toy example for predicting whether someone has the flu or not. So I have a bunch of features, cough, dyspnea, aches, weakness, chills, fever, and they have various values. Based on the model that I've learned, each of these features has some weight of evidence score. Some of these are positive, some of these are negative. So I can draw these sort of like this, where the ones with positive values speak in favor of the hypothesis. So they suggest that I do have the flu, and the other ones speak against the hypothesis, suggesting that I don't have the flu. So in this case, the height of the bars corresponds to sort of the strength of the evidence. So cough is strongly suggestive of flu. Absence of weakness slightly speaks against flu, but not very much. But absence of fever speaks strongly against flu. One nice thing about weight of evidence is that it's additive. And so to basically get the total weight of evidence for all of these features in favor of this prediction of flu, you just add up these bars. And this is now strong support for flu. Okay, so we can do this for a bunch of tasks. So in order to see whether this is useful, we conducted a user study with about a dozen professional data scientists, where we give them a tutorial where we basically walk them through the concepts. There's a bunch of knowledge checkpoints in the tutorial to make sure that they're understanding things. The tutorial is an IPython notebook, or I guess a Jupyter notebook. And then we have a main study where they're basically tasked with understanding the predictions made by a classifier on a data set they were unfamiliar with, using this tool. So I won't talk through all of the results of the study, but just highlight a few things. So the first, which is good, is that people were basically able to use it successfully to learn about the data and the classifier. And this was true even though a bunch of them struggled with some background concepts. So one of the background concepts that many people actually struggled with was this issue of base rates. So it's well known in social psychology that people make the base rate fallacy all the time. Like you see some symptoms in favor of disease, you think you have that disease, even though the prior probability of that disease is like 1 in 10 million. So it turns out that data scientists are not free of this fallacy, and many struggled with conceptualizing base rates correctly, but despite that, they were able to still use the tool. Participants used pretty much all of the modalities that we provided them. So we provided them the ability to get sequential predictions. We provided them the ability to get explanations at both a coarse-grained level and a fine-grained level. So one of the participants said that about the sequential breakdown that this was like a story of how the prediction was made. And many of the participants who had more user-facing jobs rather than developers really liked the ability to use this as sort of a storytelling so they could explain to customers what these models were doing. They really wanted the option to switch modalities interactively. So the tool we built did not allow this. So they could either sort of run it in sequential mode or run it not in sequential mode. They could run it in granular mode. They could run it in fine-grained mode. But they really wanted this to be more interactive, which is in line with, I think, pretty much everything we know from cognitive science and HCI. We just didn't do it because it was hard, and we didn't put the time into it. And I guess the last thing, which is maybe obvious in retrospect, but I think important to highlight, is that the almost all of the participants said something along the lines of the tutorial being critical. And I think this is important in contrast to a lot of work in explainable AI, where people are sort of just given a tool and asked to use it. I think like if you want to get a better sense of how people are going to actually make use of the thing, like it's important to really explain to them what's going on. So in terms of time, our study was about 90 minutes with each participant, including a post survey, and about half of that time was the tutorial. So it was a big investment, but it turned out to be really worth it. All right, maybe I'll take a pause here and see if there's any questions.
Any questions from anyone? Looks like there is no question.
All right, so then let me go on to sort of like what we're working on now, and how this sort of ties everything back into this original framing, right? So there's a lot of work at this point in sort of this explainable AI space, and I could probably plop down an entire slide's worth of citations of different ways to produce explanations, of which the weight of evidence is yet another one. There's much less work looking at what should we explain, right? So the general framing taken by almost all work in explainable AI is that if the human is trying to solve a task like content moderation, the best thing I should do is train a system to solve that task, and then give the person the system's predictions and give them the explanations of those predictions. But why is that true, right? So like if our goal is to help a human make a decision better, it's not obviously the case that trying to replicate the human's decision-making process and then showing it to them is the best way to help them. And so one direction we've been looking at is like, what should we actually be predicting and explaining? So this is a data set from Zana Businka from her IUI paper 2 years ago. So you have a picture of a food, and the person's job is to predict whether it contains at least some fixed percentage of fat. So does this peanut butter and jelly sandwich contain at least 50% of fat? So you can ask people to do this. You can also give them a prediction. So this is what Zana did, where they have an AI system that predicts the answer, and there's a typo here. It should be 50%, not 30%. And so you can show them this prediction, and you can possibly also show them an explanation of that prediction. So that was Zana's paper. But there's other things you could try to predict. So for instance, one thing that we're looking at that you could try to predict is you could try to predict, is this an example where people are going to struggle? Or an example where people are likely to make an error. So this would be more like a sort of warning. I'm not going to tell you what I think the answer is. I'm not even going to try to predict the answer. I'm just going to try to identify this as a case where I'm going to try to get the person to slow down and spend a little bit more time making a decision than a case where the system thinks that the person is going to find it easy. So this is like super preliminary results, so like don't read a huge amount into it. But we're going to look at the accuracy of the human predictions as a function of the different types of things we can predict. So the control, they get no prediction at all. Their accuracy is a little bit over 50%. The gray bar is showing quartiles, which means that in about 25% of cases, their accuracy was under 38, and in about 25% of cases, their accuracy was over about 92. We can do sort of the traditional explainable AI thing where we've trained a system to predict the actual answer. It turns out this actually doesn't help people very much. This is consistent with Zana's results. This is possibly because of over-reliance, where if the machine makes an error, the person just copies that error, or it's because they just ignore the system. Both seem to be happening in the data. Alternatively, you can try to predict when they are going to make an error, and this actually helps significantly. So their overall accuracy goes up from the high 50s to the low 70s, and their quartiles actually go up significantly. There's now very few examples on which they're more often making mistakes than not. So that was just about making a prediction. We haven't yet done the thing where we explain those predictions, but that's obviously on the docket of things to do. This is a very simple task. It has the advantage that you can give it to crowd workers and they can do something reasonable with it, but it's not the most important task in the world. So we're looking at this specifically in the context of content moderation. And there's obviously questions about how does this vary as model accuracy changes. So if you do a better or worse job predicting outcome or predicting error. As a second example, in this content moderation case, we want to be able to provide explanations or information that help the person that may not be part of the original input itself. So one of the ways that, a human machine team is going to possibly be better than a human alone or a machine alone is if they're exploiting complementary sources of information, like in this example where the machine is pulling up this other article that demonstrates plagiarism. So why is this important for classifiers? Cynthia, give me 1 sec. I'll come back to you in 1 second. So a lot of NLP tools are now built on top of these large language models, which contain a bunch of background knowledge built in, which the models are then going to use to make predictions. But it's not very helpful to explain a decision based on information that's available only to the classifier, not available to the person. So this is especially important when the background information could be wrong. So if you ask, this is T5, if you ask T5 to fill in this blank, it may say a father of 2 girls, it may say the former president of the United States. Both of these are true. You can argue about whether one is more appropriate or not, given the context. I think they're actually both reasonably appropriate. But there are other cases where when you ask it to fill in the blank, it relies too much on the context, and here produces that Thomas Bach is the Russian Olympic Committee chairman, which is actually not true. He's the International Olympic Committee president. And so actually, let me sort of skip over this slide. But basically what we want to be able to do is when the classifier is relying on this background information that comes from pre-training, we want to be able to surface the source of that information so that the person can make a decision about whether to rely on the prediction or not, based on whether that prediction is based on accurate background information versus not. Cynthia, do you have a question?
Yeah, maybe this is something you just haven't gotten up to. Maybe I'm jumping the gun on this, but a lot of the time the background information, like just looking at the examples you were giving, the background information for plagiarism is pretty obvious. You look at this thing, this is an example, but for something like moralizing or anecdotes, the actually explaining what in these large knowledge bases makes me think that's true is its own difficult problem.
Yeah, I agree. I picked the plagiarizing because it was the easiest case I could think of in that setting where the background information would be really obviously relevant. But I agree, like it's kind of the least interesting case. So I think the more interesting case are these more subtle things where the person where it's less obvious what the appropriate background information is, and it's also less obvious sort of how much of it to give to the person. And then I think you really want the interaction where the person can sort of ask for like more details. Right. But yeah, we're not there yet, but yeah, that's sort of where we want to go.
Okay, thank you.
Yeah, so let me just skip this because I wanted to sort of get to the end. So I sort of talked about these 3 aspects of trying to open up this pipeline of communication between a person and a tool that's supposed to be helping them do a better job, especially in the case where both are learning. So I didn't talk much about the learning part. That was the part that I skipped over at the very end. So I think in all of these cases, our goal really is to try to provide communication that's natural to the person and to provide information that's useful to the person in making their decision. And so the question is, how to do this in a way that helps them do a better job at their task without trying to like automate their task away. There's a bunch of stuff where you know, there's big gaps. So one big thing here is that a lot of the results that I showed you, we were only able to do in simulation because the number of interactions required to make progress is too high for my paltry crowd worker budget. And so we really need to like push on the efficiency of learning. And then the last thing is really connecting even more closely like what people need when considering the explanations that machines might give, and how to enable people to give feedback about whether a particular explanation was useful or not, either explicitly, like that was good, that wasn't good, or implicitly through asking more questions, sort of like Cynthia was getting at the end. So with that, I'll wrap up. I know we're like very short on time, but I'm happy to take more questions if there are.
Thank you. Thank you, Dr. Daumé, for the excellent talk. Any questions from anyone? Go ahead, Matt.
Hal, I have another question, which was you know, a broader question about common ground, because you mentioned that and the goal of natural communication. So when you mentioned common ground in the introduction, made me think about you know, how we should model that in interactive systems that use natural language, and possibly even Grayson maxims, because you know, in your in the work you described about clarification, if the agent knew that it should be relevant, it wouldn't ask an irrelevant question if it had a model of relevance. So I was wondering to what extent you think agents should explicitly model notions of common ground, maybe the maxims, for smooth interaction, or can it be learned implicitly in most applications? And I'm thinking of domains, task domains, where humans and agents are going to work together.
Yeah. Yeah. So so one thing we're looking at right now that's getting in this direction a little bit is something a little bit more along the lines of sort of like nudging toward pragmatics. So for instance, in the navigation setting, you know, I mean, there's sort of like, you know, I don't know if I can come up with a good example off the top of my head. But anyway, what we're sort of pushing on right now is when the person gives clarifying instructions, they're plausibly doing this with some theory of mind of the agent. And when the agent is interpreting those instructions, we're pushing it toward trying to have like, you know, sort of one of these like, they said this thing, that must mean they want X, otherwise they would have said this other thing, right? So we're right now sort of pushing in that direction. It seems like it's helping, but it's like super preliminary right now. But I think more broadly, so in terms of this broad question about sort of like structured versus less structured models, I mean, this is sort of hinted at like by my sample complexity comment, right? So I kind of believe that if we have like infinite interactions and like whatever, like sure, just throw some unstructured neural network thing at it and like maybe it'll sort things out. But like if you actually want to do this with like real people, like you don't get 10,000 interactions to like learn something. You get like 10 interactions to learn something. And so I think like if we're going to really like push that sample complexity down, like it has to be through more like inductive bias through model structure and things like that. And I think this, I think things like explicitly modeling intention, explicitly modeling common ground, stuff like that, I think that's like a super interesting direction to look. And if you have pointers, or if you want to work on this together, I would be more than happy to talk.
Sure. Yeah, I mean, there's a lot. I'd like to know. I'm still not quite sure. I don't have my finger on like what models, structured models that are useful today. I mean, if it's going to use like something like an SVM or an MDP, or is it something different from that, you know, in contrast to the transformers that you mentioned? So I'm just like, that's obviously unstructured kind of, but I'm just, you know, I'm not sure what the models are yet. And yeah, I mean, there's a lot of theories on that. I mean, in the dialogue work, there's been decades of people trying to model common ground in some way, but, you know, there's not a lot of like openly available technologies that you can use for that support it right
Yeah, yeah, for sure.
now. Thanks for your answers.
Yeah, thanks for the question. It's really good.
Thank you. Yeah, we are already past 1 o'clock. So thank you, Dr. Diamond, for the great talk. And it's a great pleasure to have you here.
Yeah,
Thank
it was
you.
great to see you all. Hope you all have a great rest of your day.
Thank
And feel free to reach out if you have questions or want to talk about anything. Like, I'm really excited about this whole direction. So anything you're excited about, please talk to me.
Thank you.